A transformer works like two friends holding the ends of a stretchy rubber band. When one friend, the primary winding, pulls and releases the band, the other friend, the secondary winding, feels the motion even though they never touch. In electrical terms, the rubber band is the magnetic flux phi that threads the iron core. A changing current in the primary creates a changing magnetic field, and that changing field induces a voltage in any nearby coil. This is called mutual induction. Faraday's law tells us that the voltage induced in a coil is E equals negative N d phi over dt, where N is the number of turns. The negative sign simply means the induced voltage tries to oppose the change, Lenz's law. The iron core provides a low reluctance path, so the same flux links both windings, making the coupling very strong, near 100%. Because the same flux passes through both windings, the ratio of induced voltages depends only on the ratio of turns, not on the absolute size of the flux. This basic picture is the heart of all transformer operation. Derivation of the EMF equation for an ideal transformer, E equals 4.44 Fn phi max. Start with Faraday's law for a sinusoidal flux. Flux varies as phi of t equals phi max sine omega t, where omega equals 2 pi f. Differentiate d phi by dt equals omega phi max cosine omega t, equals omega phi max sine omega t plus 90 degrees. The instantaneous EMF in a winding of n turns is E of t equals negative n d phi by dt, equals negative n omega phi max cosine omega t. The peak value of the EMF is E peak equals n omega phi max, equals n2 pi f phi max. In power system practice, we use the RMS value because it relates directly to heating. For a sinusoid, RMS equals peak divided by root 2, giving E RMS equals n2 pi f phi max divided by square root of 2, equals 4.44 Fn phi max. Thus the famous EMF equation for an ideal transformer is E equals 4.44 Fn phi max. It tells us that the induced voltage grows linearly with frequency, number of turns, and the maximum flux linking the core. Apply the EMF equation to the primary P and secondary S windings. E sub P equals 4.44 Fn sub P phi max. E sub S equals 4.44 Fn sub S phi max. Because the same flux phi max exists in both windings, divide the two expressions. E sub S over E sub P equals N sub S over N sub P equals. Where A is the turns ratio, secondary turns divided by primary turns. Voltage transformation rule. If N sub S greater than N sub P, a greater than 1, the transformer steps up voltage, E sub S greater than E sub P. If N sub S less than N sub P, a less than 1, it steps down voltage, E sub S greater than E sub P. Analogous to a gear train, the number of teeth on each gear determines how fast the output shaft spins compared to the input. The magnetic flux is the common shaft and the turns are the teeth. Flux phi equals B times A, where B is the average flux density Tesla and it is the core cross-sectional area square meters. Substituting into the EMF equation gives E equals 4.44 FNBA. If the number of turns is fixed, the induced voltage is directly proportional to the product of frequency, flux density, and core area. Example 1, frequency change. A 50 Hz transformer with N equals 500 turns, B equals 1.2 Tesla, A equals 0.01 square meters produces. E equals 4.44 times 50 times 500 times 1.2 times 0.0. 1 equals 1,332 volts RMS. If the same core is used at 60 Hz, the voltage becomes E equals 4.44 times 60 times 500 times 1.2 times 0.0. 1 equals 1,598 volts, about 20% higher. Example 2, flux density change. Keep the 50 Hz, 500 turn winding but reduce the core material so B falls to 1.0 Tesla to avoid saturation. Voltage drops to E equals 4.44 times 50 times 500 times 1.0 times 0.0. 1 equals 1,110 volts. Thus designers can trade frequency and core material to meet a target voltage. The ideal EMF equation assumes all flux links every turn, perfect coupling, and that windings have zero resistance. Real transformers have R1, R2, DC resistance of primary and secondary wires. X1, X2, leakage reactance caused by magnetic fields that do not link the other winding. Exact equivalent circuit per phase. The diagram shows V1 feeding series resistance R1, then series leakage reactance X1, then the magnetizing branch, then series resistance R2 and leakage reactance X2 to V2. V1 equals E1 plus I1 times R1 plus JX1, where E1 equals 4.44 times F times N1 times phi max is the induced EMF. V2 equals E2 minus I2 times R2 plus JX2. The sign differs because current lives the secondary. Approximate simplified form. When the transformer is lightly loaded, IR and IX drops are small, so we often write V1 approximately equals E1, V2 approximately equals E2, which is the basis for most textbook EMF calculations. In high power or low voltage designs, the exact form must be used to predict regulation and efficiency. Explanation: calculation of transformer turns ratio for given primary and secondary voltages. Exam type problem. Problem statement: a 240 volt, 50 Hz transformer is required to supply 120 volt to a load. Assuming an ideal transformer, find the required turns ratio N sub S over N sub P. Write the voltage turns relationship. V sub S over V sub P equals N sub S over N sub P. Insert the numbers. 120 over 240 equals N sub S over N sub P. Simplify. 1/2 equals N sub S over N sub P. Therefore, the turns ratio required is N sub S to N sub P equals 1 to 2, or N sub S over N sub P equals 0.5. If the designer chooses a primary of 200 turns, the secondary must have N sub S equals 0.5 times 200 equals 100 turns. Typical exam twist. The problem may give the primary turns and ask for the secondary voltage, or provide frequency change and ask how the ratio must adjust to keep voltage constant. The same steps apply. Use the EMF equation and keep flux constant. Given a 3-phase, 10 kV transformer rated at 400 volts line on the primary, 230 volts line on the secondary, operating at 50 Hz. Core area A equals 0.015 square meters, flux density B equals 1.2 Tesla. Find required flux. Phi equals B times A equals 1.2 times 0.015 equals 0.018 Webers. Find turns per phase using EMF equation. Per phase voltage equals line voltage divided by square root of 3. VPHP equals 400 divided by square root of 3 equals 231 volts RMS. NP equals VPHP divided by 4.44 F-phi equals 231 divided by 4.44 times 50 times 0.018 equals 57.8. Choose 58 turns. Similarly for secondary, VPHS equals 230 divided by square root of 3 equals 133 volts. NS equals 133 divided by 4.44 times 50 times 0.018 equals 34.3. Choose 34 turns. Turns ratio. NS over NP equals 34 over 58 approximately 0.586, which matches the voltage ratio 230 over 400 equals 0.575, close, allowing rounding. Rated currents power equals square root of 3V line I line. Primary current, IP equals 10,000 divided by square root of 3 times 400 equals 14.4 amperes. Secondary current, IS equals 10,000 divided by square root of 3 times 230 equals 25.1 amperes. These numbers show how the EMF equation links mechanical design phi A to electrical ratings. Explanation: common exam questions on EMF equation derivation, application, and error analysis. 1. Derivation question: starting from Faraday's law, derive the EMF expression E equals 4.44 Fn phi max for a sinusoidal flux. State each assumption made. Expected answer: differentiate sinusoidal flux, convert peak to RMS, assume sinusoidal operation, neglect core loss and leakage. 2. Application question: a transformer is designed for 60 Hz operation with a core flux density of 1.5 Tesla and cross-section 0.02 square meters. If the same core is used at 50 Hz, what is the new maximum flux density to keep the same rated voltage? Use E proportional to FB. Thus B new equals B old times open parenthesis F old divided by F new close parenthesis equals 1.5 times open parenthesis 60 divided by 50 close parenthesis equals 1.8 Tesla. Discuss why this may cause saturation. 3. Error analysis question: a 500-volt transformer is calculated using the ideal EMF equation, but the measured no-load voltage is 485 volts. Identify 3 possible reasons for the 3% error. Answers may include winding resistance drop, core loss hysteresis plus eddy, leakage flux reducing effective phi, temperature-induced resistance change. 4. Turns ratio problem: a 240-volt to 120-volt transformer has 300 primary turns. Determine the secondary turns and the induced secondary EMF if the core flux is 0.02 Weber at 50 Hz. Ratio 1 to 2 arrow secondary turns 150. EMF equals 4.44 times 50 times 150 times 0.02 equals 666 volts. Peak arrow RMS equals 666 divided by root 2 approximately 471 volts. But because of the ratio, actual secondary RMS equals 120 volts, shows the need to keep phi consistent. These typical questions test the student's ability to move from theory to quick, accurate calculations, and to recognize practical non-idealities.